All right. So yesterday, and actually sort of last week as well, I was working on a library that we have called Compressonator, and everyone's like, "Oh, why are you doing that?" And I'm like, "It's easier if we just draw a diagram." So here is said diagram. So um, we have the asset variance system. Oh, look how tiny that text is. Very life is fun. Life is fun. Where is text? How make text big? Text font size. Font size is extra large. Are we like zoomed? Like what? Excuse me? That's extra large. Oh yeah, we could zoom in and we can make. Oh, I see what's happening. If I just like refresh, will it just be like, no, it's remembering stuff. Okay, cool. Make the box smaller. Zoom in. All right, we're gonna get back to. There you go. There you go. Right, so we've got the asset variance system. Now, everyone's like, what does the asset variance system do? The asset variance system takes assets and it makes them more optimized. So let's say that you give Resonite just a PNG of a dog. We send that to the asset variance system and we say, hey, could you make this PNG of a dog more optimized? So that it's better to be rendered, it's better to be stored, it takes up less space, it takes up less memory, it's more optimal. And the asset variance system goes like, sure, but instead of just generating one PNG of a dog, it actually generates several PNGs of a dog at different formats. And it groups them all together and says like, hey, these are the variants of the PNG of the dog. And then you're able to get those and use those, and it makes everything more optimal when it comes to loading in the PNG of a dog. Now, part of that system handles any asset you can think of. The PNG of a dog is just an example, but it could also be things like a skybox or a model or a what are they called? A lookup table file or anything like that. Basically everything. One of the new assets that we're adding to the asset variance system soon is actually a Gaussian splat as well, if I can spell this correctly. Because that also can be a variant. What we're actually going to do there is basically if you give us like a PLY, we can actually convert it to an SPZ thanks to Cyro's library. SPZ is the like 10x smaller when it comes to file size, so it's a lot better. Let's make that a different color. So all of these go into the asset variance system, and all of these are computed in a different way. So sometimes it uses a library called crunch.net. Sometimes it uses a library called Compressonator that we're about to talk to. Sometimes it uses other stuff depending on what's going on. We also do some 3D model stuff that I don't quite understand, but there we go. All of this requires different libraries, and all of these libraries are basically a pain in the butt. One of the libraries that we have is called Compressonator. And Compressonator is part of the asset variance system. And it computes more optimized versions of mostly bitmaps. So PNG of the dog, like PNG, anything like an image, it computes most of that. And Compressonator is actually a two-part library. We have Compressonator.net, which is the C# portion of it. And then we have the main Compressonator library, which I'm just going to call Compressonator native. Let's add that to the dictionary. Compressonator native. Both of those compiled together make the Compressonator stuff that we're dealing with. And it's actually more like, oh dear, it's actually more like this. Like Compressonator native does the actual native compilation. .NET is just calling into the native compilation, and then it goes back to the asset variance system and goes like, hey, we're good. Now, the asset variance system has a worker, and the worker does all this work. It currently runs on a Windows VM that is part of a Linux machine. So if we go over to here, remember people asked why, and this is like the explanation. It does take a while though. It's like we've got this Linux VM, it's a Linux bare metal machine, and on the Linux bare metal machine, there's a Windows VM, and the Windows VM, the Windows VM is what's running the asset variance system. And the reason behind that, the entire reason why this runs on Windows rather than Linux is because of Compressonator. There were other libraries that we needed to make work on Linux, but the Compressonator was just the last one for some reason. And it's a problem because it's a VirtualBox machine on a bare metal Linux machine, and because we need people to have access to it, it's exposed to the internet, and so it's just unideal. The Compressonator, sorry, not the Compressonator, the Windows VM keeps crashing as well, and I do not know why. Like, it will just stop responding, and the best thing I can do is to just restart it. And so that's what I've been doing for, like, basically a year and a half at this point. I've just been restarting the Windows VM, and there we go, right? I've just been restarting the Windows VM, and it'll start up again, and it will start the asset variance system again, and it will start running again, and everything will be fine. But I'm done with that now. Like, I'm done with like that being a problem. I don't want to do that anymore. So what we need to do is to get Compressonator native running on Linux, and to do that, we needed to compile it to Linux, and we got that working thanks to the PR by a combination of J4, Yosh, and Julian, who provided all the parts together that have made us able to, for the first time in forever, we now have .so files. .so files are the Linux way of doing shared native libraries. They're called a shared object library or a shared library, or whatever you want to call it. On Windows, you'll know these as .dll files. And so when they both get combined together for Compressonator native, we now have a native version of that code that can run on Windows and can run on Linux. So once this works, and that does now, thanks to this, you can see those files there, we just have to integrate them into Compressonator.net. Once they're integrated into Compressonator.net, the entire Compressonator flow will work on Linux, the entire asset variance system will work on Linux, and then I'm going to take this Windows VM, and it's going to be yeeted into the next galaxy, because I hate it, and the asset variance system is then going to run on Linux. Once it runs on Linux, I'm also going to give it some performance tweaks, because it will then be on Linux, and we can do a little bit more. This will include additional metrics about what's going on. To explain that, I'm going to grab another tab for a second. Hopefully this maintains its use on the recordings and on the screen share, so I'll double check. Yep, it has. Right, so if we scroll down to asset variance system here, you see this number keeps going up and then will go down again. Usually that's when I notice that it's crashed and I've restarted it. In fact, if we go to our max length right now, which is, that'll do, but it'll run off. You see, like every single time this is going up, it's like, particularly this kind, where there's a slow build up and then like it burns off. That is when the VM crashes. So we gotta fix that. Additionally, if you notice, if we zoom in here, let's go to this area. There's been a general baseline of jobs stuck on the asset variant queue at around 10,000. And you can see that dipped last couple of days down to 8,000. These items, this 10,000 and this lower part, are in what's called the poison queue. The poison queue are assets that have been through the variance system once or twice, and then an issue has occurred, or the job took too long, or something went wrong. And what that does is it means like, hey, this is a problematic asset. we'll shove it into the poison queue, and what that's meant to signal to us is process the poison queue separately and with more scrutiny, with more inspection, to sort of see, hey, what's wrong? Why is this in the poison queue? And then we can fix bugs of that. The problem is that some of those bugs are, we think, in Compressonator. You can take a look at the GitHub, and I'll get some links to the issues at the moment, but there is a couple of bugs to do with HDR images, reflection probes, and even skyboxes that are causing people's CPU to go to like a bajillion%. And we think that this is lying somewhere in this area, right? Compressonator, Asset Variance System, Compressonator.net, Compressonator.native. We can't figure that out because we don't have a good workflow for making incremental changes to the Compressonator library. So in order to get that going, what I wanted to do is to get it building so that if I did have to make changes to the source code of the native library, I wouldn't be stuck, right? I could just PR to master, and then the GitHub actions will kick off and we'll get .so files back off the stack. If you remember back in the day when we had an issue with free image, there was a critical security vulnerability over in free image. We had to do all of that work then to like try and figure out how to compile it. And that was like extra work. We've done that ahead of time. So if we do a bunch of diagnostics and why reflection probes are doing all this, or HDR images are doing all of that, the goal is to make it so that the entire Compressonator Asset Variance System flow is easy. And that includes being able to deploy the Asset Variance System worker dynamically, and being able to say, hey, update and deploy and only run the poison queue. Run the poison queue now for 3 hours, then run the regular queue. Let's deploy 2 copies of it. One running the regular queue, one running the poison queue. Let's run the regular queue with less logging and the poison queue with more logging. All of this stuff is what we can do by moving it to Linux, because once it's on Linux, those who are aware of how Linux works, etc., it's like one step away from Docker. And once it's on Docker, it means I can spin it up and pull it down incredibly quickly on as many machines as is necessary. So like, let's say we suddenly get like a 10x viewership base jump, or we have a lot of stuff that needs assets to be computed, MMC, wink, wink, then we can scale it up or scale it down beyond just the one machine. We could take this this Linux bare metal machine, and we can have 2 of them. We could have 3 of them. We can have 1 million of them. There's also these systems that might not be Docker. There might be other container types. It doesn't really matter. Like once it's containerized once, we can easily containerize it in another container system that will allow us to not deploy these to bare metal servers anymore. We can basically give the Docker file to Azure or other container managers, and they'll say, sure, we'll run your container on our machines, provided you tell us what it needs. And I'll basically say, hey, we need a lot of CPU. Here's our container. They run the container, and then we don't need to manage the actual machine. It just handles it for us. And so we have a big event, MMC again. We need more compute. We can just go, hey, here's a container, run it. That's the goal, and that's what's going on. And that's why what the work that was done by J4 and Yosh and Julie, which was basically, it was like one sentence that like unlocked everything. So I'm so happy about that, is making this next part done. This part I've pretty much got like established, like I know what I need to do. Yosh has some stuff there to help me out, but I'm pretty sure I know what needs to go on there. Once this works, I will then be running the Asset Variance System on Linux on one of my Linux machines just to sort of see what happens. And everything looks good, we'll be able to move forwards. And you should never, ever, ever again see the Asset Variance System queue being high in the alerts channel, or at least that's the goal. When I do the update, I'll also add a bunch of additional metrics that we'll be able to see. I'll be able to give you things like how big the poison queue is, the type of the queue as well. We'll see like graphs that sort of show like, hey, the queue is processing 500 bitmaps a second, but only 200 models a second. That's interesting information. Stuff that could help us sort of figure out what's going on. It can also help us alert better. We could basically say like, hey, the failures on this specific type of asset are increasing. Let's fire an alert to the alert channel. Instead of the alert channel being Q is high, shrug. It'll be the Q of this specific type of asset is high. And then we can go, great. And then we can go check the logs, which will also be updating. And it will say, here is the problematic asset. Here it is in the logs. Here's what the problem is. We can fix it. And then that alert will go away. I think that's all for this diagram. If anyone has any questions, let me know. But I'm going to go through the rest of the questions that appear. And I think we're done with the diagram. Hope that was useful.